So we've been talking about simultaneous localization and mapping. Most recently, we've been talking about scan matching and how we can use the data from a LiDAR successive scans to kind of piece them together to create either a map or at least register scans from one to the next. And we've talked also about the grid, using an evidence grid to do this mapping, but we haven't talked about a critical thing, which is bilinear interpolation. So I'd like to start out to talk about linear interpolation and how we just interpolate between points of data, basically filling in gaps. And here is an example of, we know some points here. There's a point at 140, there's a point at 150. What if we wanted to know what the value was at, say, 147? Now, here are those 2 points right here. Again, here's 140, which is this one, 150, of course, is there. And we see these values. We can look those up. The XY value is 140 is 0.6428, 150 is 0.05 or 0.5. And so the way we find a point in between, which is right around here, if we're going to do linear interpolation, we basically look at the difference, the local change in both X and Y, and then we solve that problem for Y equals MX plus B. We solve that little problem so that we can come up, if we have the number 147, well, what's the proper value? And to do that, you can see is here's M, which is the slope, is just the difference in Y over the difference in X between these two. And that's what we're showing here. There's a difference in 10, that's the X difference. And there's a difference of a negative 0.1428. So it's going down for a positive run in X, okay? And again, by doing that, we can then say, well, if we take a new point, 147, we subtract the beginning point, which is 140, so that's number is 7, times the slope, but then we have to add back that 0.6428 to get the answer here of at X equal 147. And you can see here, we do the math, we just plug those numbers in and multiply that divided by that, times that, plus that, then gives us that the Y value at 147, when taking a linear interpolation between the 2 points, is 0.5428. Okay, now this is actually a sine wave, so there's actually a little, instead of a straight line between the points for 140 and 150, it's actually slightly curved, but you can see that that's essentially straight there. And that's what linear interpolation is. It just says, hey, we're just going to assume it's a straight line between them. What would it be? Okay. Now, we can do the same thing on a grid, just like our evidence grid, with bilinear interpolation. That means you need to do it both in X and Y, and we're going to do the exact same thing. But we're just going to have to do it twice. And so it's a little bit more complex, but not too bad. So you can imagine you have these 4 grid points, okay? And this could be 140 and 150, right? And then, whatever the size is. But keep in mind, now it's X and Y with a Z value that they're indicating in each one. So there's an X location, a Y location, and then Z, a magnitude of whatever is inside the cell. And that's the example here, I of 1, 1, I of 1, 2. That's kind of the magnitude of the cell. And then, we may have 1, 1, 1, 2, 2, 1, 2, 2. In order to find some value here that is some distance X away from 1 and some distance Y below, or I'm sorry, we're increasing down and to the right. So some value y from 1 also. The question is, what is that value, right? I of p, which is not completely in I21. It doesn't appear to be in I11 or I12 at all, right? But it is influenced by them from their center points, right? So we do the same thing. We assume a linear interpolation between the points IPX1 and IPX2, and then we can figure out where those are. And then, so what that does is across the I11 to the I22, that's X. And then we're going to do the same thing top to bottom to find what the actual value is between the two. Okay. And we see here that we take the H. So we computed the so this is both the H value and the W value, and then we plug it in to get the final number. And you can see it's kind of a messy equation, but it's no different than mx plus b. And you can see that it's w minus x over w times some value x over w. Again, these are ratios. Just like we do, and we can solve this for any value now using a formula, this simple formula. We know the H, we know the W, we know the X, we know the Y, we know those values. We can just plug it in and interpolate. Okay. In our grid, we have occupied, and we have our three values, right? We have occupied, a barrier, and unknown. So occupied, unoccupied, or unknown. Now, what we're talking about being able to do, for the reason we're looking at bilinear interpolation, is we might want to have confidences associated, odds associated of what the probability is of something occupied, what's the probability that it's unoccupied. And then that's when we might want to do this bilinear interpolation. We have a point here where we're really sure it's occupied, or maybe we're not so sure. We think it's a little bit occupied. Here's another point. Yeah, it seems to be unoccupied. Now, how do we then interpolate between them across this grid? Okay. And that we're going to use here in this Hector slam, where we're having the LiDAR does the pre-processing on say, on the LiDAR data. It then does scan matching on successive values in order to either look at a map or relate it to a map. And then there's this navigation subsystem also down here, which we haven't yet talked about, which is where are we going to go? And then how are we going to control the robot to actually get there? So we're really focused right now on just how might you actually take the LiDAR, pre-process it, sort of figure out where we are and how intermediate frames are related. So that gives us, for example, equivalent of odometry. If we can figure out, well, how much did we move between frames? That is an estimate of odometry, actually. And then we can say, well, where is that, say, in a given map? And those are the things we're going to be talking about.